Hey guys, welcome to AI with AI. This side Asif Himnad. Today's video is really interesting. Trust me. We are gonna talk about all the machine learning algorithms and we will be comparing all the machine learning algorithms to demonstrate using the famous Iris dataset. As this video is going to compare all the machine learning algorithms, that is supervised machine learning algorithms. If you do not have time now, watch it later when you have a time. Okay, so this video will help you understand how machine learning algorithms perform on same Iris dataset and how do we tune parameters to get better accuracy. Eventually, this is what the beauty is. This is what the task of ML engineer, data scientist is to get the better accuracy using different machine learning algorithms and decide which one to choose for this specific dataset. All right, let's get started without wasting our much time. And we will be starting with the very small and simple example so that you guys can also implement. Okay, so this is all about Iris dataset and it's a typical machine learning classification problem, right? So what we need to do here, there are three species of the flower, that is setosa, versicolor and virginica. That's an iris flower, right? So we need to predict given three species of the flowers to the model, train that model on given data, and when any new flower is given, find out which type that new flower falls into, whether it is setosa, versicolor and virginica. Definitely, we won't be having photos here. That's part of image recognition and feature extraction. That's a part of deep learning. We'll see that later in the deep learning series. But for now, let's focus only on the machine learning part, right? How do I get the data here? So we have a data in the table, okay, in the numerical form. Definitely, even if you extract the features in the computer vision, when the image extraction happens, it actually looks at the features and puts them into the numbers. This is what we are doing manually here. For now, we don't have the image extraction. So we have a data in the table where we have sepal length, sepal width, petal length, petal width, and the class label as the column. What do you mean by the sepal length? So the lower part of the flower is called sepal. So we have sepal length and the sepal width given, and we also have the upper part which is called the petal, right? So this is petal length and petal width is given. So if the sizes of the flowers, petal and sepal length, the measurements are given, based on that the prior data is given. So if it is sepal length is 5.1, sepal width is 3.5, petal length is this and petal width is this, then this flower is a setosa. So this data is given. So this is supervised learning, right? So the measurements, that is x column, x values, and the y values, that is output, is also given. So we have a correct data already. In supervised learning, right answers are given already. We need to find more right ones. So in future, when I receive new flower measurements, I need to find out which class it belongs to, setosa, versicolor or virginica. Simple. So what steps we are going to follow? Let me quickly tell you the steps. It's very simple, right? We have already seen this. Prepare x and y. X is your input, y is your output. Supervised learning, right? We have right answers given. You need to find more right ones. And once you prepare x and y, next step is to choose which algorithm you want to use. That is import machine learning algorithm. So once you choose which algorithm you want to use, you will train the machine learning model on the input. So you will be training your machine learning model. We have a simple method, if you remember, that is called model.fit, right? So once you initialize your algorithm, then you'll be training this, that is model.fit. Once the machine learning model is trained, now your model is ready to predict based on the new input given. Okay, so these are the simple 4 steps that we guys are following in machine learning so that we can easily see the demos, easily see the examples on it. So this is super easy. Okay, so these are the 4 steps that we follow. Other than this, we are gonna also see a model.score so that I can check what is the accuracy of my model, whether it is 90%, 92, 95, whatever. Okay, so let's jump on the demo. Please focus only on the cells which I'm executing. Okay, so this is the first cell that I want to execute. I use shift enter to execute these cells. Okay, so what we are doing here, ignoring warnings, importing panda, matplotlib and seaborn. Okay, so these are the 3 data science libraries which are required to plot the data to find out the insights of the data so that I can understand what is the nature of the data, right? Based on that, I can take the decision which algorithm I should use, which algorithm is the best fit. This data is already we have in the CSV format, right? I kept it in some directory. I am reading that data. So this is how the data looks like, and iris.head. So this is iris is our data, and I'm reading only the head. That means first 5 rows, right? So you can see sepal length, sepal width, petal width, and the class of that flower. Going ahead, so what I did here, I have got data frame, right? If you don't know about basic data science Python libraries, I urge you to understand pandas, matplotlib, seaborn, numpy. So these are 4 basic Python libraries that everyone must understand, right? Iris variable is a data frame here so that I can perform operations on the table. Okay, now once I have the data frame, let's see what are the total counts I have. I mean, how many different types of flowers I have. I have 50 setosa, 50 versicolor, and 50 virginic. I mean, we have 150 rows here, and all are of type integer, and we are doing the count on the species only. Okay, so I just wanted to understand if the data is not biased. Yes, and data is not biased. We have 50-50 each. So let's train our model and use logistic regression here. But before doing that, I just want to see how does my data looks like. So because there are 3 types, there are 3 classes, right? And how do they look like? So to see how does the data look like, I'm using a scatter plot here, and this is the part of seaborn library. If you check, we have imported seaborn as SNS. So I'm using sns.facetGrid, iris, the data frame, and I'm using map function here to plot petal length and sepal width here. So you can choose whichever columns you want to highlight here, right? We can visualize, we can plot only 2 columns, right? So for now, just for understanding purpose, how does the data look like? I am plotting this data on petal length and sepal width. You decide on which you want to plot. Okay, so you can see there is a simple classification available, right? Blue ones are separated, the orange and green are a little bit mixed with each other, but these can still be classified with the line, right? There will be outliers. There will never be 100% accuracy, that's for sure. We'll get 100% accuracy for this blue, right? What is this blue? Setosa. For Setosa, we should get 100% accuracy. That I can bet by just looking at the data, because there is no mixing of blues into the other types. So I can see the legions. Blues are the Setosa. Versicolor is orange, Virginica is the green one. There is a bit of a mix here in the versicolor and Virginica, so I may not get the 100% accuracy for versicolor and Virginica, but for Setosa, I'm damn sure that we should get. Okay, let's see how it goes. Now what next? So machine learning doesn't understand these words, right? So we will map these words, that is Setosa, versicolor, Virginica, into the numbers, that is classes. Class 0, class 1, class 2, and these numbers are nothing but Setosa, versicolor, Virginica. Okay, so let's map this by using map function here. Iris species column, map it to flower map. Flower mapping is nothing but this dictionary. Okay, so mapping is done. So now I have a new column ready with 0, 1, and 2. So finally I have X and Y ready here. So this is the first step that we follow. Prepare your X and Y. X is iris dataset, that is data frame, sepal length, sepal width, petal width, values. I need values of these 4 columns. And what is your output? Y is your output. And what is the output? The species is the output, right? Data frame, species, values. Okay, so X and Y is prepared. What is the next step? Next step is import your algorithm. So we are using scikit learn, import logistic regression. It's very simple. Once you import, then initialize, right? Model is equal to logistic regression, open close rounded bracket. So this is the default initialization for now. There are also some of the tuning parameters you can pass here, but let's keep that aside for now. We are initializing with the default values. So once you initialize, now we are good to go for the next step, that is to train the model and find out the accuracy, or to predict the output for the new values. Okay, so to train, it's model.fit. It's that simple. So training happens behind this model.fit method, model.fit function, right? Unlike linear regression, when you do model.fit, it draws a line, but not to best fit, but to divide the data into 2 parts, right? So all that drawing of line and dividing that data into this different part is happening behind this. Drawing a best division line here, and division line maybe here, it will be done by machine learning. so that when new data point comes, if it falls here, that means it will be a setosa. That's how it will be predicting the output for the new data set. Simple. Amazing, right? Okay, let me execute this. So my model is ready. Let me check the accuracy. And how do we check the accuracy? We have a simple method called score, right? Model.score, provide x and y so that you can see what is the accuracy you have got. So it's 0.9733. That means we have 97% accuracy. Okay, though it is not the correct way to measure the accuracy of the model. As we proceed in this series, I will tell you how do we measure the accuracy and how can we make our machine learning model better and better and tune our machine learning model so that we get the better accuracy and reduce the noise. Okay, but for now it's very simple, right? Model.fit, model.score. And now let's do the predictions. So to do the prediction, what I'm doing here, I have a simple method model.predict and I'm passing x values. Though I'm passing same x values, let's see what is the prediction I will get for the same input which I have used for the training, right? This is the same input. I'm not giving any new input here, but the ideal scenario would be provide the new input so that you can get the actual predictions here. But for now, I don't have any new inputs. I'm going to give the same input which I have given during the training. That's again the x. Okay, now let's see what is the prediction I'm gonna get here. Okay, so the predicted is this for this given input. So for 150 data set, this is the output I have got. So if you remember, we have mapped our characters, that is classes setosa, versicolor, virginica, into zeros and ones. That's why I'm getting output in this way. By looking at this, we don't really understand, right? So what exactly happened here, whether it is correctly predicted, whether it is not predicted. So to understand this output or a prediction in a better way, I have something better matrices that is called confusion matrix. It will give us the insights of the predictions. Okay, for that I'm using sklearn matrices. Okay, so let's import matrix. I'm printing the matrix report expected and predicted here. Expected is nothing but your y is actual output. Against the actual output, what is your prediction? That is what I have given here, expected and predicted. Let's execute this. If you see, I have got something called precision recall F1 score. So this is a better way to measure your accuracy. Okay, rather than score, you just understand 97% of accuracy you have got. But you don't really see the insights of the predictions, right? By looking at this, you can understand that for the setosa class, you have precision 1, recall 1 and F1 score 1. That means you got 100% accuracy. Do you remember? I told you just by looking at the data, it's very easy to classify the setosa flowers, right? If you draw a line here, it is very easy to classify this. There will not be any confusion here at all. We'll have a confusion here because there is a mix between these two types, versicolor and virginica measurements, right? Let's see that what the precision recall and F1 score says. For the class 0, that is setosa, it is 100%. For class 1, versicolor, we have 98% precision, 94% recall and 96% F1 score. What do you mean by precision recall F1 score? We'll understand maybe in some other videos, but for now you can just say that these are the better ways to calculate the accuracy. Alright, then for second type, for the class 2 virginica, we have 94% precision, 98% recall and 96% F1 scores. So people will look at the F1 score in general, right? For now, just to understand, you can say that F1 score is an average of precision and recall. So people will always ask you for what is the F1 score of your model. Okay, F1 score is a better measure for accuracy. F1 score for setosa type is 100%, for versicolor is 96 and virginica is 96 again. Okay, and this F1 score is derived from precision and recall only. It is always better to give the model's accuracy as F1 score. Okay, this is what the F1 score stands for. I have one more measure to understand the output, the prediction, that is called confusion matrix. Once you import matrix, you have classification report and you also have a confusion matrix, right? So matrix dot confusion matrix, expected and predicted. Okay, let's execute this. What do I get? So I got the matrix here. What I see, 50 0 0. 50 means, if you remember how many data points we had 50 classes each, right? Setosa 50, versicolor 50 and virginica 50. So 50 out of 50 predicted correctly for setosa. That's what I understand from here. 50 0 0. No wrong predictions. For virginica, I can see 47 are correctly classified, whereas 3 are classified as virginica. So machine has predicted 47 correct versicolor. 3 versicolor are classified as Virginica, which is wrong. What about this? If you see here, 0 are classified as Setosa, 1 is classified as versicolor, right? Whereas 49 are classified as Virginica. So 49 means there are correct 49 data points classified as Virginica. Only one is wrongly classified. So by looking at this, there is a 100% prediction for Setosa, and there is a very bad prediction for second type, that is versicolor, and even there is a good prediction for versicolor. Simple, right? So this is how I can understand what is the prediction that I have got by looking at the confusion matrix. So just to give you an idea, so naive Bayes is a simple and very effective algorithm which can be used in classification problems. So this is our classification problem, right, which falls under supervised learning, where we want to classify different types of flowers. So here we don't really use these equations. Machine learning uses these equations internally. We will be just importing these libraries and getting the predictions, getting the classifications done on the Iris dataset. Some more information on naive Bayes algorithm. Naive Bayes assumes every feature, every input is independent. On this data, we will train our model. This time we will be using naive Bayes classifier. There are 3 types of naive Bayes classifiers we can use, right? Gaussian naive Bayes, multinomial naive Bayes, Bernoulli's naive Bayes. We're going to use all these 3 algorithms and we will understand which one fits best for our dataset and which gives better accuracy. And we are importing one more library, that is Gaussian naive Bayes. That's the only one thing that we have added here. Okay, sklearn.naive Bayes import Gaussian naive Bayes. So we will be using Gaussian naive Bayes algorithm to start with. So if I see the data, this is how it looks like. Okay, petal length versus petal width. Alright, if you observe this closely, the blue dots are way far than the other two. So we can see the clear classification here. Just by visualizing, I can easily say type 0, I mean this could be Setosa, can be classified very easily. So there is no mix and match here. But for type 1 and type 2, we have some mixes here. So there may be a poor prediction for classifying type 1 and type 2's, versicolor and virginica, but for type 1 we can see 100% accuracy just by visualizing the data. Let's see what machine learning gives us. Alright, so that's it. We visualized, data science part is done. Now simple task is model we are going to use is Gaussian naive Bayes. Model is equal to Gaussian naive Bayes. Model.fit. It is simply we are training our data. It is that simple. Machine learning is very easy. Everything is ready. We just have to use the functions. We just have to use the algorithms. Alright, so I'm using model.fit. Iris.data is X and iris.target is Y. X and Y, we provide both input and output to our machine learning model. And this is what we call training our model. So model training is done. I'm using simple score function here to see what is the accuracy of my model. So model.score, input and output again. We are currently checking it on the same data. On the same data, what will be the score? Okay, so on same data, the accuracy is 96%. 0.96 is nothing but 96% accuracy we are going to get. Okay, but remember, this is on the same data set. So the accuracy may be different when you provide new input. So for new inputs, I'll have to prepare different text here. Okay, but we know that score is not a correct way to measure the accuracy of our model. So that's why we use precision recall and F1 score. For measuring the accuracy accurately, we are going to use metrics. So for this, I'm preparing X and Y again. Expected is nothing but our target and predicted is nothing but model.predict. So model.predict will actually give me the predictions. So in simple words, once the model is trained, we use model.predict and we provide new data. Currently we are providing same data here, but in reality we provide new data so that it will give us actual output or actual predictions. Let me execute, and now I am using metrics library to display the confusion matrix and precision and recall. Let's hit enter here. So how it looks like, you can see precision, recall and F1 score, and 0, 1, 2 are the classes, right? This is Setosa, this is versicolor, this is virginica. Alright, so we see the precision, recall and F1 score for type 0 is 111, and we have already identified it just by visualizing it. It can be easily classified. There is no mix, right? So that is why precision for this is 100%. 1 is 100%, and precision recall for type 1, it is 94%, recall is 94%. That's why F1 score is 94%. In layman's term, F1 score is nothing but average or mean of precision and recall. Okay, and versicolor type 2, 94, 94. That's why F1 score is 94%. Alright, so this precision recall and F1 score gives us the better understanding of the accuracy of our model. So accuracy of our model is 96%, right? And we are also displaying it using confusion matrix. And this is how the matrix look like. I don't know why people call it as confusion matrix. It's very easy to understand. Let me help you here. It's a 3 by 3 matrix because we have 3 types, 3 classes. That's why 3 by 3. How many data we have? We have 50 type 0, 50 type 1, 50 type 2, right? 50 out of 50 are rightly classified as setosa, that is class 0. Simple. And in row 2, we can see 47 are rightly classified, that is type 1, versicolor, and 3 are wrongly classified as virginica. Okay, so we see 47 data points are classified as versicolor and 3 are wrongly classified as virginica. This gives us more insights, isn't it? And if I check third row, we can see that 0 classified as setosa, 3 classified as versicolor, 47 are rightly classified. These 3 are wrongly classified as versicolor, which is actually a virginica. These must be virginica, but it is wrongly classified as versicolor. Important is to understand which algorithm to use when. Important is to understand how to make our data machine learning friendly. That is really important. And improving the accuracy over the period of time. That is really important. So we all know the decision trees is supervised learning method where the right answers are given, where we have a labeled data, we need to find more right ones, right? So it is a classification and also sometimes a regression task, and it is one of the most widely used classification technique in machine learning. Now let's use decision tree classifier and provide this data, train this data, and find out the accuracy. So next step that I'm gonna do is use decision tree classifier. Okay, and model is equal to decision tree classifier, model dot fit, nothing different. It's very simple. Even for any other machine learning algorithms, if you remember naive based classifier, logistic regression, so we used a one single method, that is model dot fit. So fit function here is nothing but it is training our model. It is looking at the data, finding the correlation and trying to understand the data, and I'm providing x and y. So iris dot data is my x and iris dot target is my y here, right? So we have trained our data. Let me hit shift enter. Okay, and model dot score is again an inbuilt function which will give us the score of our model, iris dot data and iris dot target. So this is on the same data, it is not something different. Okay, and when I get 1, that means there is 100% accuracy. Whoa, this is something amazing. A decision tree classifier is giving me 100% accuracy for iris dataset classification. Then why should we not use decision tree every time? Then this is the only classifier I should always think of using. Why there are other classifiers? We have SVM, support vector machine. We have logistic regression. We have naive based classifier. We have random forest classifier. Then why all these different machine learning algorithms we have when decision tree can give us 100% accuracy? So as a machine learning engineer or a data scientist, this is what you need to understand. Which machine learning algorithm we should use on what data? Which machine learning algorithm fits best for what type of context, for what type of domain? So by looking at the data, you should understand that this is the machine learning algorithm that I should think of using, which will give me a better accuracy. So our end goal is always to get the maximum accuracy, but we are getting 1, that means it is 100% accurate. Okay, so let me do the predictions now. The accuracy that I'm getting on the training data, the same data that I have used to train my model. Now let me see the better accuracy by using matrix algorithm, that is confusion matrix, precision recall and F1 score. For that I have 2 more variables I have created. Expected, that is iris dot target, that is y column. This is what we expect, 100%, right? This is what we expect, that is y column. And predicted is nothing but what is the final output that we have got, what is actually predicted, right? Model dot predict and x column. Okay, so what is predicted and what is expected? We got 2 variables and we're gonna pass these 2 variables. Let me hit shift enter first to execute this cell, and in this cell what we are doing is matrix dot classification expected and predicted, matrix dot confusion matrix expected predicted. We're just trying to understand the better accuracy, the better way to measure the accuracy of our model, right? And quickly precision recall and F1 score helps me understand the accuracy better. So it says for type 0 I am getting 100% accuracy, that is precision is 100%, recall is 100%, F1 score is also 100%. F1 score is actually average of precision and recall. Okay, and for type 1 it is also 1 1 1. For type 2 it is 1 1 1. So that means again I'm getting 100% accuracy in terms of precision recall and F1 score. I told you there is a twist here, we'll talk about that. And what is the confusion matrix? So if I look at the confusion matrix here, if you remember how many rows we have 50 rows, right? We have 50 of each type, 50 setosa, 50 versicolor, 50 virginica. Okay, so this confusion matrix says 50 are rightly classified as setosa, 0 versicolor, 0 virginica. So this second row says that the type 1 is rightly classified. This is type 0, type 1, type 2. Okay, this is setosa, versicolor, virginica, right? So again, this tells me that there is no misclassification. The machine learning training is so accurate that we are getting 100% accuracy. So that is why we need to understand the pros and cons of machine learning algorithms. And it is also important to understand what are the parameters that I can think of using in machine learning algorithms, right? In the model that I'm going to use, that is decision tree classifier, I should know the parameters. I should know how should I fine tune my algorithm. Okay, so to do that, you don't really need to remember. Okay, you can just Google decision tree library and look at the library so that you can able to understand the parameters better. So for this decision tree classifier, you can see the parameters, that is criterion, splitter, max depth, max samples, so on and so forth, right? So if you remember, we discussed about criterion based on which you want to split the features, based on which you want to consider, because decision tree creates a tree, right? Root node and the leaf nodes, so on and so forth. So what is that criteria by which you want to split the attribute? So default is Gini index. We can change it if you want entropy, log loss, so on and so forth. We can switch between Gini index and entropy. If you don't want, you can keep default. You can also think of using splitter. It is just to understand which node needed to be considered as a best. How do you want to split your attributes, whether by using a best match or a random approach? Not much important. For us, the important one is criterion and the max step. So you always remember one thing, decision tree has a tendency to overfit. So if you don't cut the tree, if you don't define the max step, it will keep forming the tree. So when you form a tree, that means you will always end up getting the right answers. Okay, so I told you about one disadvantage, and which is very important, that is decision tree has a tendency to overfit. All right, so that is why we need to define the depth, through to which depth you want to create the tree, and you don't want to go further, because if you do not define the depth, then tree will be completed and you will get the pure nodes at the leaf always. That is why you will always get 100% accuracy. So let's go back to our demo and define the parameters here. So you can see the one line that I have commented. Let me comment the previous line here, hash, and let me remove this. Model is equal to decision tree. I'm defining criterion is equal to entropy, because default is anyway Gini index. We discussed entropy as well in previous video, right? And max depth is 3. I want to create the tree only till the level 3. After that you can cut the tree. Don't allow tree to grow. That is what we are saying here. Okay, so let again execute this, and now let's see what is the accuracy we are getting. Let me execute all the cells here. Okay, so if I come back and see, I can see that the score this time is 97%. Beautiful. Okay, after I define the depth, I cut the tree, the accuracy got reduced. And it is important to define the depth, right? And this is where the machine learning engineers, the data scientist job is to understand the best max depth and the best criteria. This is what you mean by fine-tuning your parameters, fine-tuning your model. Okay, and what is the confusion matrix and precision recall F1 score we are getting? It is 1 1 1 again for setosa. You remember we have already discussed it. When we have plotted the data, it was pretty easy even for us to classify it. Okay, so there is no mix match between any other classes, so definitely we will get 1, that is 100% accuracy for type 0, that is setosa, whereas we had some mixes in versicolor and virginica. That's why I see 98% precision, 94% recall, and F1 score is finally we got 96% for type 1, that is versicolor. Okay, similarly for type 2 it is 96. So in general we always give the accuracy of our model in terms of F1 score. So we say F1 score of my model is 96% here. All right, and looking at the confusion matrix, I get more detailed analysis. I can say the setosa is classified 100%, that is 50 setosa, 0 versicolor, 0 virginica. And on type 1 we have 0 setosa, 47 are rightly classified as versicolor, 3 are wrongly classified as virginica. So there are three data sets, three flowers, which are actually versicolor, but these are classified as virginica. Okay. And third row says that 0 classified as setosa, 1 is classified as versicolor, and 49 are classified as virginica. So there is only a one false prediction here. Okay. Whereas for versicolor, there are three bad classification. Okay. So let's change the max depth of our model and see what is the accuracy I'm gonna get. This time I'm gonna change it to 2. Let me hit shift enter again. Let's see the score. So now this time it is 96%. Previously we were getting 97%. Now also let's see the precision recall F1 score and confusion matrix. So again, there is no change in setosa, 100% accuracy for this, right? Versicolor virginica 94. So this time my model accuracy is approximately 94-95%, right? And I can also see the confusion matrix. So this time the confusion matrix is bit different. So there are 5 wrongly classified virginica. Okay, so 45 are virginica and 5 flowers are wrongly classified as versicolor. All right, so this is what I can predict. The conclusion from this discussion is you should always define the criteria and the max step. Okay, let's proceed ahead. This is just for fun. I have extended this demo and created some visualization. Okay, let's hit shift enter for now and let's see what we have, what is interesting here, what is fun here. It is nothing different. We are just using some interactive Python libraries and we are trying to interact with our model. We are trying to provide the parameters and see how does my machine learning algorithm is trying to classify the data here. Okay, so if you look at this, so here we are using two interactive widgets, that is type and depth. So in the type you can see you can choose the parameter, right? Gini index or entropy. So by using Gini index and defining the depth, I can change the depth of my model. So accordingly you can also visualize. You can see the below diagram is changing for sepal width and sepal length. Amazing, isn't it? On below you can also see when I define, let's put it as Gini index and change the depth, max depth to 2, and you can see the precision recall and F1 score here, right? It is 50, 49, 45, and when I change the max depth it should also change. Now this is different, 50, 47, 49. It is just for fun to play with the decision tree algorithm and provide the dynamic parameters. Okay, but all we did is a decision tree classifier. The parameters we are dynamically providing, nothing different. You can see there is a function defined. We are just passing the values at runtime. That is all. Quick overview on random forest. Random forest is an advanced version of decision tree where a big data or a huge data is split into smaller data sets, and every part of the subset will have individual decision tree, and finally takes the average from all the decision trees to predict the accuracy of the data set. Just to conclude, rather than having a one decision tree on a huge data, we will have a split of a data and having multiple decision trees on individual data sets. And finally something like this. So you can see you have tree 1, tree 2. So we have 6 trees here created from the same data set, and we'll take a decision from individual trees. So this tree says yes, this tree says no. We see most of the trees are saying yes and only one tree is saying no. So here we take majority vote. Random forest takes the majority vote and predicts the final output. So the output would be finally, it will be yes. In simple words, huge data divided into the smaller data sets. Every data set will have an individual tree. Individual tree will calculate the result, and finally taking the vote from all the trees and based on that predicting the output. This is what random forest does. Alright, let's jump on the demo part now. So I am importing random forest classifier. Forest, a variable, is equal to random forest classifier. There are certain parameters. Let's see what are the different parameters we have. So random forest is derived from decision trees. So multiple decision trees are nothing but the random forest, isn't it? And if you remember, if you know, in decision tree we require depth of the tree. We need to decide the criterion of the decision tree, whether you need to split the attributes by Gini index or you need to split the values by entropy. So this is the machine learning classifier we are using, random forest classifier, and some of the parameters here. So let's quickly understand these parameters. I'm just gonna Google random forest sklearn. Let's open it. Okay, you can see the random forest classifier and the parameters. Number of estimators, default is 100. How many trees you want to create
from the data set. Do you want to create 10 trees, 15 trees, 20, 100, whatever? Default is 100. Criterion, how do you want to split the attributes? As I've said, gene index or entropy. And also max depth is required. That is, what is the depth you want to keep for the trees? You need to cut the trees, right? Why do we cut the tree? I mean, why do we define the max depth? Is basically to avoid overfitting of the data. Overfitting and underfitting is the regularization technique. To avoid overfitting, we are defining the max depth. We need to cut the tree, and similarly so on and so forth. There are multiple different attributes that you can see here, but we don't really need to understand all of these. First three are important one, and this is sufficient. If you want to read more, you just Google and open the Scikit learn library. Okay, coming back here. So in the random forest classifier, we define criterion as gene index, and number of estimators is 5. Basically, we want to create 5 trees from this data set. Depth of the tree is decided. Each tree depth will be 2, and then further simple steps. Train the model using fit model.fit, which is forest.fit. Provide x and y. X is nothing but input. Dataset.data, this is where I have the input. Dataset.target, this is where I have the output. This is x and this is y. So my x is actually all the 4 columns, 1, 2, 3, 4, and y is the target column. Okay, so this is what we are providing here. Model.fit, forest.fit, and then looking at the score, basically looking at the accuracy. Let me execute this. So the score is 96%. So that means I'm getting 90% accuracy. Okay, so this model gives you 90% accuracy. Beautiful. Amazing, right? So I can just play with these parameters and check the accuracy further. If I change the max depth to 5 and number of estimators, that is, let's say if I want to create 10 trees, let's see what is the accuracy I'm gonna get. So you see accuracy is increased, but we should always cut the tree. Let's see if I make it 10, doesn't make any difference. If I make it 1, yeah, accuracy is changed. It is 97% accuracy I'm getting here, score I'm getting here. We are good. So you just play with this. We need to have the fine-tuned model to predict the output, right? And furthermore, we just want to see precision recall and F1 score to better understand what is the accuracy we are getting here. To find how our model is performing, we are using metrics. Okay, now what next? We can use this trained model to predict the future inputs, right? So you prepare the data. So currently I'm using same data. Iris.data is the same input that I have provided. So you can imagine here we have prepared new data set, new Iris data, a new flower type we want to predict. We provided that here, and we are predicting. Forest is basically a model.predict new data. I'm just printing the output here, so it gives me array. You just need to provide one row. Even one row is sufficient to predict the one flower. Okay, or provide the table to get the array, something like this. Okay, so on provided data, this is what the output we are getting. 0 is setosa, 1 is versicolor, 2 is virginica. Now to understand data in the more detail, we are further looking at the metrics of the data, that is precision recall and F1 score. Let me catch what is expected and what is predicted. So expected is nothing but my actual target, iris.target, and predicted is nothing but forest.predict iris.data. Basically, after prediction, what is the predicted output you got? This is expected output, predicted output. So I have prepared my variables and providing these variables to metrics classification report. To get the report, basically to calculate precision recall and F1 score, I'm passing expected and predicted, and also I want to see the confusion matrix. Specifically, we call this as confusion matrix. So let's see how does my confusion matrix looks like. Okay, so the matrix looks something like this. Precision recall and F1 score looks something like this. So you can see for type 0, that is setosa 111, we are getting 100% accuracy, 50 data set, and all of them are rightly classified. Type 1 versicolor is precision is 94, recall is 98. F1 score is basically average of precision and recall. For F1 score of our model for type 0 is 1, for type 1 is 96, and type 2 is also 96. Alright, and the total accuracy, if I see, is the 97%. Okay, so F1 score of our model is the 97%. This is what I can conclude by looking at the matrix. And furthermore, we are looking at the confusion matrix here. So confusion matrix gives us detailed overview, detailed insight of the data. So we have 50 setosa type flowers, right? All are rightly classified. 0 classified virginica, 0 classified as versicolor. Whereas this row tells me about how many of these are classified as versicolor and how many of these are classified as virginica. So 49 versicolor, 1 virginica. And third row talks about type, that is virginica. So 3 are wrongly classified as versicolor and 47 are rightly classified as virginica. Beautiful. All right, I hope you understood how we are using random forest classifier, and we have also understood how we are using different metrics to look at the insights of the data to accurately find out the precision recall F1 score and to find the actual accuracy of the model by using confusion metrics. Shift enter to check the plot of the data. This is how the data looks like, and very simple to understand here. We want to classify the data based on the target. That's why the hue selected here is a target, and the DF is where your complete data is available. If you can see here in the graph, type 0 is very far from the other data points. Blue data points is basically 0. You can see the legends here. Orange, amber one is 1, and green here is 2. So blue is setosa, amber here is versicolor, and green here is virginica. So just by looking at the data, I can easily say I may get 100% accuracy. I mean, type 0 can be classified very easily, that is setosa, whereas for versicolor and virginica there is some mix. Greens are mixed with the orange data points here. So drawing a classification line on such data points is a bit difficult. However, I draw the line to classify this data, I may not get 100% accuracy. Okay, this is what I understand by looking at this. Okay, let's proceed ahead and try to apply support vector machine on this data set. svm.svc has some parameters, so these are called tuning parameters. And these parameters are very important. We need to understand the parameters and the importance of these parameters. Otherwise, demo is really easy, right? Just import svm model.fit and model.predict and your machine learning model is ready. The important here is to understand why support vector machine, and important here is to how support vector machine by tuning the parameters and what are these parameters. Okay, just to understand what are the parameters here and what is the value that I should provide in the parameters, I need to Google these parameters. Let me Google scikit-learn svm library. Let's scroll down and understand the parameters part. You see C is very important. C is a regularization parameter. You might have seen value of C or parameter C in some of the previous examples as well, such as logistic regression, right? So it is a regularization parameter which will help you fine tune your machine learning model. For simplicity, I'm gonna tell how the value of C is gonna affect the support vector machine here. To quickly understand what is C parameter here, so whenever you provide the value of C, if it is large value, it needs to be a positive always, it above 0, and as you provide bigger and bigger value of C, the margin will be smaller. It is inversely proportional to the margin. So the larger the value of C, smaller is the margin. Smaller the value of C, larger is the margin. By looking at this diagram, I can easily understand that I should not provide bigger value of C, because larger the value of C, smaller is the margin, and it will have a tendency to overfit the data, right? It will be as good as logistic regression, drawing a classification line so that it can classify the data. Then what is the difference between support vector machine and logistic regression? Logistic regression also draws a line to separate the data, but the importance of support vector machine when it keeps the margin. Okay, so the margin kept here is decided by the value of C. So you need to find the tuned value of C. It should not be so big and it should not be so small, so that you should not also have an underfitting. So identifying that value of C is really important, and it should be positive. Let's go back to scikit-learn and understand different parameters. Now the second most important parameter here is the kernel. Kernel parameter is really important. Kernel defines what type of support vector machine you are gonna use. Is it linear, polynomial, RBF, sigmoid, pre-computed, so on and so forth. What type of kernel you want to use. Just to quickly give you idea about what is this kernel stands for, I'm back on the presentations here. Sometimes the data is not linearly separable. You cannot draw a line to separate the data, to classify the data. I cannot draw a line like this to classify the data. I cannot draw it like this. I cannot draw it like this. Then how should I classify this type of data? This is where you need to understand that this is not linearly separable problem. And this is where you need to look into different dimensions and come up with a different idea, that is kernel SVM. So it tries to look at the data in different dimensions and tries to draw a hyperplane, something like this. As you see in the diagram, data is drawn against the axis, so that now the data looks something different, and from top this is how the data looks like, and the hyperplane is somewhere here. Whenever the data is not linearly separable, we use kernel SVM. So you need to define what type of kernel you want to use for SVM model. That's why really important. For our example, we'll be using linear and also RBF here. Then there are some more parameters. You can try these out. Just one of the parameter that we will be using is gamma, and gamma is generally useful when data is not linear. I mean, whenever you set value of kernel as poly, RBF and sigmoid, this is where gamma value will come into picture. I'm gonna provide value of gamma and we'll see how it looks like. Okay, let's go back to our demo. Great, I hope now these parameters are clear to you. So to start with, I'm using linear kernel and value of C is provided 1. It can only take positive numbers. Let's see, and we can change the value of C here, and model.fit X and Y, iris.data, iris.target. Okay, shift enter. My model is ready, model is trained. Everything happens behind the scenes with simple one function, that is model.fit. And finally, to look at the score, how my model is performing, I can use model.score, iris.data, again X and Y. Basically, we are providing X and Y again just to check how my model is performing on the same data set here. So I can see the accuracy is 0.99, which is 99%. Amazing. Let me change the value of C here. So does it make any change on the score? Let's see, shift enter again, 0.1 this time, model.score. You see it is 96% now, right? So value of C has been changed. It is again positive, 0.1 I have provided, right? It should not be a large. Now you can understand even 1 can be a bigger value for C, okay, based on your data set. So you need to just try out by using different values for C. So if I provide 0.1, which gives me lesser accuracy, which is 96%. So should I use 0.1 or should I use 1 here? What is the best value that I should put for the C? But let me explain, bigger the value of C, higher the chances of overfitting. So that is why you see better accuracy. But better accuracy doesn't mean your model is good. It is overfitting. So you need to find the best fitting value. So let me put 0.1 for now, and let me do the further predictions so that I understand the insight. Just by looking at this accuracy, I don't understand how does the data is really classified. So I'm gonna see precision recall and F1 score, and to check that I have prepared expected and predicted here, and let me execute this cell as well. So this cell will give me confusion matrix and also classification report. I'm using metrics here. So metrics gives me precision recall and F1 score, right? Expected and predicted. Expected we already have, which is a target column, and model.predict will give me the predicted values based on the data that you're gonna provide. This is Y and this is predicted after model is ready, which will be available after model.predict. These are the values I have provided to the different metrics function here, so that I got precision recall and F1 scores. So this gives me better insight. 0 Setosa, 100% accuracy. We have also seen this here in the diagram, right? There should not be any problem with classifying Setosa. I can draw any linear line here and classify this. So 100% accuracy. For versicolor, 95. F1 score is 95. So this is the accuracy I'm getting. And I can also see that here because there is some mix of Setosa, that is orange data points here with the green. So that is why I got 95%. And for versicolor, 95% F1 score. F1 score is the average of precision recall. And if I look at the confusion matrix, so this is my confusion matrix here, which shows me row 0 is Setosa, row 1 is versicolor, row 2 is Virginica. 50 rightly classified as Setosa, 0 wrongly classified as versicolor, 0 wrongly classified as Virginica. Whereas row 2 tells me about versicolor, 0 wrongly classified as versicolor, 48 rightly classified as versicolor, 2 data points are wrongly classified as Virginica. Whereas row 3 tells me that 47 are rightly classified as Virginica and 3 data points are wrongly classified as versicolor. Okay, this is how I can understand the insight of the predictions by using confusion matrix. Really important technique. Okay, you can change the value of C, you can change the kernel and look at the different values that you're gonna get here. But I'm going one step ahead here to change the type of the kernel to non-linear. How does it perform when I have non-linear data? If I change the kernel type to RBF, how does this look like? I also want to visualize this. So let's try that out. You don't need to really worry about the code. I'm gonna provide you the GitHub repository link for this code, but what we did here is, again, we prepared X and Y Iris dataset. We are considering only first two features, first two columns. We also want to visualize the data, right? To visualize the data, only two-dimensional data can be visualized. That is why only two features, only two columns. Let me show you the output first so that you guys can understand what I'm trying to explain you here. So if you see, this is how my data look like, and I have tunable parameters here. These are I widgets, interactive widgets. If I change the kernel currently provided is linear, and I have tunable parameter which can be changed using interactive function. If I change this, do you see the diagram below is also changing? This linearly separable line is also changing. Please observe that as I change the value of the C, that line is also changing, isn't it? Do you see that? So larger the value of C, it is overfitting. Smaller the value of C, it is underfitting. So I need to find the trade-off between this. But most importantly, we need to check the other kernel type, which is RBF. So I'm gonna select RBF here, and value of C doesn't really matter in RBF. So let me keep it as it is, and I'm gonna change the gamma. Gamma becomes really important in case of RBF kernel, where we are thinking, why I selected RBF is because I'm thinking my data is not linearly separable. That's why I'm using RBF kernel. And let's see how does the data looks like. So currently gamma value is 50. So I can change this value. Let me make it smaller. You can see as I'm providing smaller values, the classification is also changing here. Please observe that. It will take some time because there is a small delay here, but doesn't really matter. You see the value of gamma is 1 now. This is how the classification is happening. This is non-linear. That is the importance of RBF. We are visualizing how SVM is working in non-linear kernel. Amazing, isn't it? Let me change the value of gamma. Let me make it bigger, and let me see how does the SVM really classifies the data. You see, bigger the value of gamma, there is overfitting. So don't provide bigger value of gamma here. It is going overfitting here. So some of the data points are missed. SVM model is trying to draw a separation for every data points, which is overfitting obviously. It is always better to choose the good value of gamma. I think 10 is enough. I hope now you understand what is RBF kernel and what is the value of C and what is gamma. Let me quickly talk about how it is working. What we did here is we just created a function, mySVM classifier, and this function is getting called by the interact function. So whenever you are changing the value of kernel C or gamma from this, every time it's gonna call this function, and dynamically we are passing the parameters kernel, C and gamma. Whatever value of kernel you provide here, it will call this function. Okay, every time you change it, it will call this function. As well as I change the value of C, it will call this function and it will draw the plot. This is what we are doing. Change the value here, call this function and draw how it looks like. And to use interact function, you see I'm using IPY widgets, import interact SVM classifier. This is the function we are calling, and the parameters which you want to pass dynamically. Kernel value linear or RBF. Drop down. Value of C is in between 0.001 to 10. Value of gamma is between 1 to 100. So these are the values I want to pass to the interactive function, and based on the value that you provided, it will call this function and draw the plot based on the value that you have provided. This is what we did here. Let me talk about KNN in short, what it really means and how KNN works. KNN is a supervised machine learning technique, most of the time used for classification problems. It can also be used for regression, but most of the time used in classification. So how does the KNN algorithm works? It is so simple. First, decide how many neighbors you want to ask to. Okay, the value of k is nothing but number of neighbors we want to calculate, we want to consider. Then calculate the distance from the new data set, from new data point. Once the distance is calculated, now the KNN will know who is nearer to the new data point, what category, what class it belongs to. Based on the count it gets belongs to the category, new data point will be assigned to the category for which the number of neighbors is maximum. And that is it. Our model is ready. Now decide which algorithm to use. KNN we want to use. So I have already imported KNN. Now I'm gonna use k nearest neighbor, and the parameter I'm passing here is 3. So how many neighbors you want to consider? Currently I'm considering only 3 numbers. Let's see how it looks like. Model is equal to KNN. Neighbors passed as 3. Hit shift enter again to train our model. Model.fit x and y, which is iris data and iris.target. Iris is my data set. You can see it here. So this is the data which I have loaded. Once the training is done, now identify the score, the accuracy of your model by simply using model.score. Let's hit shift enter. So the score of our model is 96%. So the accuracy I'm getting is 96%. Oh, amazing. Let me change the number of neighbors. 3 is bit less. It needs to be odd number. If you remember, even number is not a good idea. Let me put 11. Let's see. We have 150 data points. So 11 looks like good number. Let me execute again. Now this time the accuracy is increased to 97%. Okay. Let me change the value of K and C. If I provide 7, what is the accuracy I'm gonna get? 7 is also fine. 97% I'm gonna get. Let me provide 31 probably. Let's see. Again, this is 96%. Just for your information, you can change the value of the neighbors. This is called the parameter tuning. And default metric, the distance which is used here is a Minkowski. This is just for your information. You can change it to Euclidean or Manhattan if you want. Doesn't really matter. Default is Minkowski. But as you guys know, that score is not a correct way to calculate the accuracy of our model. That is why we are going one step ahead and calculating the accuracy of our model, that is precision recall F1 score, and also printing the confusion matrix to understand more insights. Okay, how do we do that? I'm using metrics for this. Metrics.classification report, metrics.confusion matrix. So we have imported metrics initially, if you remember here, sklearn import metrics. Very simple. Classification report will print precision recall and F1 score. I need to pass expected and predicted. So we have prepared expected and predicted. Expected is what? Target. It is y, iris.target. The predicted output that we have got. So model.predict will give me the predictions for the new data points, the new data set that I'm gonna pass here. Okay, so predicted, expected is prepared. I passed it to classification report to know the F1 score. Also, we want to print the confusion matrix here. So let me hit shift enter. This is how the report looks like. So you see precision, recall, and F1 score is printed for every category. Precision for seto size 1, recall for seto size 1, F1 score for seto size also 1. F1 score is kind of an average of precision and recall. So generally, machine learning engineers, the managers, clients will ask you for what is the F1 score, what is the accuracy that you have got. So generally accuracy is asked in the form of F1 score. So for versicolor, precision is 92, recall is 96, F1 score is 94. For Virginica, precision is 96, recall is 92, F1 score is 94. 100% accuracy for Setosa, that is what we see here. Further, if you look at confusion matrix, how do we read this? Row 0 talks about type 1, that is Setosa. Row 1 talks about versicolor. Row 3 talks about Virginica. So column 1 prints 50. So out of 50 data sets, 50 are rightly classified. Setosa, 0 versicolor, 0 Virginica. And we actually identified it visually when we printed the data here. So classifying this Setosa is a bit easier, but classification of this is not easier. It is way away from other data sets. Features of Setosa are way different than this versicolor and Virginica, isn't it? Whereas for versicolor, you see 48 are rightly classified, 2 are wrongly classified, 2 are classified as Virginica. And for Virginica, you can see 46 are rightly classified and 4 are wrongly classified as versicolor. Amazing. So there is nothing much here in the demo. So the most important part that you need to remember is import KNN and provide the number of neighbors. That is it. Remaining all the steps remains as it is. There is no difference from other machine learning algorithms. Alright, that is it for this video. I hope you understood how can different machine learning algorithms can be used on a same dataset. The more importantly, the tuning of parameters is what the conclusion is, what the takeaway from this comparo video. And I hope it also helped you to compare different machine algorithms if we have same dataset and which is the algorithm that we should use to get the better accuracy. Perfect. We are investing a lot of efforts, time in these videos so that we can give you as much as possible for free. So we expect something you to give us in return. That is simple. Just like and subscribe to this video and share with your friends so that YouTube algorithm will be happier and it will also help our channel to grow. Thanks a lot. Take care. Bye bye.